Today we have Adam Kowalski with us. Adam is one of the, I think, the latest CU NSO joint appointment here in Boulder. He started in August 2016, so hasn't been on the job for very long, and we've already got him here to give a talk for us. Before his position here at CU Boulder, Adam was a postdoc at the Goddard Space Flight Center, and before then he got his PhD at the University of Washington, Seattle in astronomy. And today he's going to give us a talk on solar and stellar flares. Unfortunately, as you've noticed, there's no coffee. The coffee will be a little bit late, so we're counting on you, Adam, to keep us awake for the first 10 or so minutes of the colloquium.
All right. Well, first, thanks very much for coming today and having me talk about flares. I'll show some movies of some flares to keep you awake in the first 10 minutes. Today I'm going to talk about one particular aspect of solar flares and other stars. We refer to them as stellar flares. And that is the white light continuum emission. The white light continuum is possibly the most important part of the flare because that's where most of the radiated energy comes out. White light just means the radiated continuum from the near UV through the optical, and sometimes also it's observed in the far UV and in the infrared. So I'm going to start by first going over a brief review of solar flares and then jumping into a new project with IRIS where we're finding new constraints on the white light continuum emission. Then I'm going to jump into flares from active M-dwarf stars, and the abbreviation I use is DME there, dwarf, M, and then E means H alpha is an emission when it's not in flaring. It means it's really magnetically active. For both M-dwarf flares and solar flares, we run radiative hydrodynamic models, 1D models, but we get detailed spectra that we can compare directly to the observations to see if we have all the physics right in our models. And I want to focus on a new result, our new prescription for modeling the electric pressure broadening of the hydrogen lines in flares. Finally, I'll get into a little speculation about what these big flares from M-dwarfs mean for nearby planets. All right, so this is maybe my favorite movie of a solar flare. It's two-ribbon solar flare and taken in by the Solar Dynamics Observatory, AIA, 171. So this is just looping through and showing you the plasma at about 800,000 Kelvin. This is an M-class flare, and so it's not even the biggest type of flares on the sun. The movie in the upper left is a different wavelength, another UV wavelength, but it's zoomed out to show you the size of this flare. So this temperature actually shows the two main features that show up in flares. First, the bright footpoints early on, right there, and then the loops later on, later in the flare. So there's the footpoints, and there's the loops. And there's some order to this chaos. There's first motion of footpoints in this direction, as you'll see. That's early in the flare, and then there's motion separating from each other. So the footpoints or the ribbons separate from each other later in their flare just as the loops start to light up. So this is terminology I'll be using, footpoints, primary footpoints and loops. The footpoints come from deeper in the atmosphere and the loops from higher. So there's been some really great multidimensional modeling of reconnection and flares recently. This is a movie by Takasao-san. It's a 2D MHD flare simulation. They simulate reconnection and the collapse of the magnetic field lines. So I'm going to play it here, and the color is the density. So magnetic field lines reconnect at the top, and then they retract at about the Alfvén speed, and then you have increase in density in the loops. So you see downflows there, which is called a condensation. And at the beginning, you actually see upflows, right, at the outer edges of the reconnected magnetic field lines. So there's downflows, condensation, upflows. We call that evaporation. So field lines become reconnected higher and higher, and the separating footpoints that you saw in the previous movie is attributed to field lines, the progression of the reconnection going higher and higher. So this movie actually shows you the increase in density progressively further and further out, just like in the movie. I just want to mention that these models don't include accelerated particles. And we know from observations that there's a lot of energy in accelerated particles and flares. So you can imagine that this becomes even much more complicated if you were to put in the accelerated electrons and ions, protons. I'm not going to talk about 3D models, but some models that have been successful in explaining the footpoint motions are the slipping reconnection models, and some references there. So the observational signature of these accelerated particles and flares is traditionally the hard X-ray emission you see. And the hard X-ray emission can come from the top of the flare loop, but the brightest hard X-ray emission comes from the footpoints, where the magnetic field lines go into the lower atmosphere. So here's a typical X-ray spectrum during an X-class flare. It goes from 10 to several hundred keV. And there are two components. There's a thermal component at lower X-ray energies, and this can be fit by with a temperature of several tens of millions of degrees. And that's attributed to the loops that fill with hot plasma later in the flare. But there's also a power law component at higher X-ray energies. And I have that labeled as the power law, and that can explain the hard X-rays. That's attributed to a non-thermal Bremsstrahlung radiation as the electrons spiral down the field lines from the reconnection site, wherever that is, and then they impact the lower dense atmosphere as they interact with, via Coulomb collisions. They emit this hard X-ray Bremsstrahlung. And that shows up as the power law component here. So from this power law, you can actually infer some parameters about the electron beam. We call them beams, electron beams, because we think, well, at least the standard flare model says they originate in the corona. So we call them beams, these non-thermal electrons. And you can get some information such as the distribution with energy, so the power law index, and then the total power and the non-thermal electrons, which is really important. So then you get a power, and if you have an area, a flare area, so all this electron power goes into some flare area, you can get an energy flux in non-thermal electrons. And that is in ergs per second per square centimeter. And in the modeling later on, we refer to this energy flux by an F number. So an F11 is 10 to the 11 ergs per second per square centimeter. So it's just an area averaged energy flux of non-thermal electrons. So how do these non-thermal electrons relate to the white light emission? Well, it's been known for a long time observationally that the hard X-rays and the white light emission are spatially coincident and also temporally coincident. So here's an observation of a flare on the limb of the sun. The limb is the solid line you see there, and the cyan contours are the hard X-rays, and the red contours show the optical emission, and the optical emission is often used as a proxy for the broad continuum emission. So they're spatially coincident, and they come from lower in the atmosphere. The orange shows the soft X-rays, the loops that fill with hot plasma. And the bottom right, here are the light curves for each of those components. The soft X-rays gradual, peaking later in the flare, because it takes a while for those loops to show up at those temperatures and fill with the hot plasma. And the white light, as the red, peaks at about the same time as the hard X-rays, the black. So we think there's some physical relationship between the hard X-rays and the white light. And the possible relationship is that the same electrons that produce the hard X-rays also heat the chromosphere and produce the optical emission. So that's the working hypothesis we'll test shortly. The best way to characterize the white light continuum emission is with spectra around the Balmer jump. The Balmer jump is at 3646 angstroms, and it's the recombination edge of electrons, free electrons recombining to the n=2 state of hydrogen. And what Balmer jump spectra can give you, the two physical parameters. One is the optical depth, and the second is the charge density. And it's important to know what the optical depth and the charge densities are at about 10,000 degrees Kelvin. It turns out it's pretty easy to heat material in the chromosphere to 10,000 degrees Kelvin, but it's really hard to heat material that's dense to 10,000 degrees Kelvin. So here are two Balmer jump spectra, one for a solar flare on the left from the 1980s, and then one of a M-dwarf flare on the right. The wavelength range of the solar flare spectrum is shown as the red bar at the top. So for M-dwarf flares, we have a much broader wavelength characterization. And so we can understand observationally, at least, the continuum emission much better than, for example, with an HMI intensity. And so the blue line in the M-dwarf flare spectrum shows a black body fit, and we typically get a temperature of about 10,000 degrees. So black body about 10,000 degrees, explaining the blue continuum, and then going to the red wavelengths. But then you also see that the black body can't explain all the continuum. At the shortest wavelengths, there's excess continuum above that, indicated by the red vertical arrow. And we attribute that to Balmer continuum emission. Yes?
The active region chromosphere doesn't have significant optical depth in the Balmer continuum?
That's what we can figure out with these spectra.
Well, I'm saying the quiet.
Oh, the quiet.
Well, not
no,
quiet,
it's very optically thin.
Yeah.
Yeah.
And so you get a tremendous enhancement.
You get a tremendous enhancement of the Balmer continuum compared to the continuum modeled as the blue curve there. So as the optical depth increases at 10,000 degrees, what we call Balmer jump ratio decreases. So the amount of Balmer continuum indicated by the red divided by the continuum modeled by the blue curve, that ratio gets much smaller.
Do you have any quiet sun spectra or anything for comparison there on the left?
For the solar flare?
No, for the comparing the flare to a quiet.
So the gray is the non-flaring spectrum for the M-dwarf. So the M-dwarf is really red.
Okay.
And then during and then so during the flare it becomes very blue.
But that's for M-dwarf. I'm talking about the on the left.
Yeah. So the actually the quiet sun spectrum or the background pre-flare has been subtracted from that.
Okay.
Yeah. So that's only the flare.
I'm just curious whether.
So the increase is about 10% at the reddest continuum wavelength, and about 100% at the far blue. So you also see there's bright emission lines in the flare, and those are the hydrogen Balmer lines, and they get really broad. And I'm going to go into our modeling for that. So from the Balmer jump ratio, you get the optical depth at 10,000 degrees. If it's small, there's a large optical depth. If there's low optical depth, then the Balmer jump ratio is really large. And then from the broadening of the hydrogen lines, you get the charge density. All right, so the three questions we're after. The first for solar flares. First, what are the observational characteristics of the continuum emission? Does it originate from the chromosphere, from the upper chromosphere, from relatively low densities? So you have an optically thin hydrogen recombination. spectrum and a large Balmer jump ratio? Or does it originate from the upper photosphere where it's denser and you'd expect black body-like emission? For M-dwarf flares, it's been well observed for many years, pretty much starting from Hawley and Fisher in 1992, that the continuum distribution is approximately 10,000 Kelvin black body with a little bit of Balmer continuum emission in addition to that. So how do you produce such heating at very large densities to produce a hot black body spectrum? Could it be a chromospheric compression? So electron beams hitting the upper chromosphere and compressing that region by a factor of 10 while still keeping it hot at 10,000 degrees. Or do you have direct heating of the upper photosphere and heating it from 3,000 degrees for an M-dwarf to 10,000 degrees? So those are two extreme possibilities. So what are the observational characteristics? Is it hot black body or optically thin Balmer continuum emission? And whatever it is, whatever the properties of the continuum emission are, do high flux electron beams reproduce those properties in models? And that's interesting because there are other possible heating mechanisms in flares which aren't as well characterized as the electrons. These other mechanisms don't show up in the hard X-rays. And these heating mechanisms possibly are ions and protons, or energy transport from the corona to the chromosphere via Alfvén waves. So first, about solar flares. We don't have the ability to take spectra around the Balmer jump anymore readily. We've tried with current instrumentation, but instrumentation is limited to, which is high spatial resolution, which is great, but very narrow spectral range. So we go to IRIS. IRIS is the imaging interface region imaging spectrograph. And although it wasn't a flare mission, it has observed many flares in solar cycle 24, including several X-class flares. So it takes data in the far UV around carbon-2 and silicon-4, and in the near UV around magnesium-2. The near UV is particularly useful to us because it's just blueward of the Balmer jump. So the Balmer jump is at 3646 angstroms and magnesium-2 H and K, and the nearby continuum is at 2800 angstroms. So this is another way of characterizing the Balmer amount of Balmer continuum in flares. So in the movie I'm going to play, the top images are the slit jaw images. The two to the left are in the far UV, and the one in the upper right is the near UV, and the slit is shown as the vertical black line there. And you'll see the flare ribbons or flare footpoints develop across the sunspot and across the slit in the movie here.
Adam?
Yes.
Before you start,
Sure.
On the left middle slit jaw picture,
Yeah.
does that include both the channels?
Yeah, that should.
Do you have
It's
silicon
carbon-2, and I don't think. I believe. I actually don't know.
It's probably one of the silicon.
Yeah,
channels.
yeah. Yeah.
It's the same detector.
Carbon-2, and then. Yeah, it's just if we chose to display them or not.
I mean, you've got the same artifacts, the same dirt fingerprints on the detector there on both. I don't know if IRIS alternates putting the spectrum.
Yeah, it doesn't take the two slit jaws at different wavelengths are not taken simultaneously.
Yeah.
So they don't kind of.
Okay. It's just one camera.
So the carbon-2 lines are 1335, and then there's the spectrum there goes to 1420, I think. Yeah, 1410. In the near UV, you can see the magnesium-2 lines get a lot brighter during the flare, and also the continuum right there jumps up. So it's that continuum increase we want to characterize. And we also have excellent spectral resolution, so we can characterize the emission line profiles to connect the continuum properties to the velocity field in the flare chromosphere. So we started our analysis of the best studied solar flare ever, the March 29th, 2014 X-class flare. Best studied because it was observed by so many satellites, instruments, and ground-based observatories. There's been, I think, 8 or 9 APJ papers and several more other refereed papers about this flare. Anyways, I'm going to start with the emission line analysis and then talk about the continuum. So we noticed that in all of these singly ionized lines, silicon-2, magnesium-2, and all the iron-2 lines that pop into emission in the near UV, at the brightest locations in this flare, well, the continuum was brightest. These emission lines showed 2 components. So I'll just talk about the pink spectrum and the iron-2. But you can see the 2 components in all the rest. So the pink spectrum has an emission component centered at about the rest wavelength. And the rest wavelength is indicated by the vertical dashed line. And then as you go to the red, there's another maximum. And this is a redshifted component of the iron-2. So that's bright in the pink spectrum, and it's fainter in the black spectrum. But it's still there. So the black and the pink spectra are just 2 different locations where it was really bright. And then you can see for the other chromospheric flare lines, there are 2 emission components. So these redshifted components were, we thought, at first glance similar to the redshifted H-alpha emission that has been traditionally observed in solar flares for decades. And so we called this redshifted component the red wing asymmetry, or RWA. I'm going to abbreviate it as that. So in addition to these bright and highly complex emission lines, the continuum got really bright at these locations. And the continuum level is indicated by the horizontal dashed lines there. The pre-flare level is this level here, which is the lowest intensity spectrum on the plot. So a factor of at least 5 increased. So to understand these chromospheric flare lines and the continuum formation, the near UV continuum formation, we needed to have a spectrum from a model to directly compare. And the best code for that purpose is the RADYN code, which was not originally written for flares. It was written by Mats Carlson, and then through various PhD theses through the decades has been modified to include flare heating and various aspects that are important for understanding flares. Most recently, the RADYN flare code published in Allred et al. 2015. Why this is the code that's most suitable to our purposes? Well, there are 2 reasons. One is that it has an adaptive grid. And so when shocks form during our flare simulations, it can resolve these shocks. And it's important to resolve shocks because we need to accurately model the mass motions, which are driven by shocks. The other strength of this code is that it calculates the detailed spectrum. So it solves the equation of radiative transfer using hydrogen, helium, and calcium-2. And if we want other transitions, other spectral lines, we use the RH code. So it has a way to model a flare. And you can put in any type of flare heating you want, but it calculates the Coulomb collisions from a non-thermal electron beam. And it does this in a pretty sophisticated way, using the Fokker-Planck solution to the distribution function. We need to prescribe the electron beam, though. It does not simulate reconnection. It does not simulate the acceleration of particles. You say you have this much energy in your electron beam inserted at the top of your model coronal loop. And then it calculates the energy loss as those electrons interact with the atmosphere. So we prescribe the parameters of the electron beam. And one of the most important parameters is this F number, so the energy flux in the electron beam. And we have constraints on that from RESI and from the flare footpoint sizes. So RESI observed the March 29th flare, and there are various estimates of what this electron energy flux could be, from 10 to the 11 or F11 to several times 10 to the 11 or several F11. And so we run a series of simulations that bracket the range of this energy flux. We run an F11 and a 5F11. And here are the results comparing to the observations. So the observed NUV continuum intensity on the left has a value of about 2-ish. And that's pretty bright. And it also had redshifted chromospheric lines. If you equate that to a velocity of about 40 kilometers a second. So the F11 model we ran didn't produce very bright continuum emission, about 0.7, so a factor of 3 lower, and hardly any redshifts in the chromospheric lines, so no highly asymmetric red wings. But the 5F11 did a much better job. It produced very bright continuum intensity, and the chromospheric flare lines were shifted by several tens of kilometers a second. We also considered a coronal heating model. It produced redshifted lines, but very faint continuum emission. So the 5F11 was the most consistent. It got much brighter in the continuum and in the lines, but it swept through the range of our observations. So a little bit more about what happened in the RADYN model. This cartoon summarizes the important aspects. So the F11 beam is inserted at the top of the atmosphere, and the code calculates how the beam loses energy. The electron beams hit the chromosphere and deposit most of their energy at the top of the chromosphere. They heat it to 10 million degrees in less than a second. So as a result of that, you have very steep temperature and pressure gradients, which form these shocks. The upper shock draws material up into the loop, so that's the evaporation. And the lower shock draws material downwards and compresses the lower atmosphere. And that's referred to as chromospheric condensation. These terms, evaporation and condensation, have been used in flare modeling for decades, since George Fisher et al., his models in the 80s, and even earlier than that. So with the RADYN code, we have a contribution function. The contribution function tells you where the emergent intensity is formed in the atmosphere. And so we can trace back the emergent spectrum, the asymmetries, and the bright continuum emission to where it's formed. And we find that the bright continuum emission in the 5F11 model is formed over 2 flaring layers, which is something it's a new addition to this standard picture here. There is a dense downflowing layer, which is the condensation. It's a little over 10,000 degrees. And that's the compression caused by the shock. So this layer is actually being compressed, and it's flowing downwards at about 50 kilometers a second. And it's sweeping up material below it. The material below it is also heated, and it's heated by the highest energy electrons in this beam. The highest energy electrons have the most energy, and they can travel the furthest before getting stopped. And those electrons go all the way to these layers here, heat it to 10,000 degrees. So the condensation is sweeping up this layer, but the emergent continuum is coming from both. So the density is really large in this condensation, but it's not dense enough to produce an optically thick continuum emission. We find that the near UV continuum originates over a low optical depth and is Balmer recombination radiation. So low optical depth, Balmer continuum, and the 5F11, even though it gets really dense and hot.
So can I just want to give a little perspective. The F11 is about twice as much as the energy per unit area as the sun radiates from the nuclear interior. So by the time you get to F11, you've already got twice the amount of energy coming down as you have coming out through the photosphere by sigma t to the 4th. And then the other thing is you're using a simple stratified model of the chromosphere, right?
It's not very simple. It's calculated self-consistently.
No, I know,
with,
but what I'm saying is you don't bother with nonsense like spicules and stuff.
No,
So,
no. It's an equilibrium.
Right. So,
yeah.
So I want to point out that I've forever run into people that keep telling me how important these spicules are and how fibrils are important and everything else you can ignore is not the chromosphere. What you're modeling is exactly the chromosphere, namely the region between the photosphere and the corona that differs by 4 orders of magnitude in pressure. And I am just so sick and tired of people telling me about fine structure of the chromosphere being the chromosphere. That's factually incorrect. That's a naive interpretation of what you see. And I'm not talking about you at all. I'm talking about this. But so what you're doing is doing exactly what I would do, which is put in a stratified layer and look at it react. And so I'm very happy about that. The other thing is, I want to know what the power spectrum of the radiation you're assuming is, because that determines how the energy is distributed and where it's distributed.
Yeah.
And then I don't know if you're going to show the distribution functions for energy deposition with depth as a function of things like energy F11, F10 or F11 versus the other ones.
I don't have
Those
any.
are really important for the behavior of this thing, and that was known since Fisher and people, right?
Yeah. So unfortunately, I don't have a plot of that, but it's something that comes right out of the model, and we can plot it as a function of time.
But basically, you're dumping energy into something that's got 9 pressure scale heights to go through, and so this thing is just going to relax according to that. And then the last question I had is that shock is propagating down. Presumably, there's not a lot of momentum going with the electrons.
There isn't, no.
So you basically have an overpressured bubble in the top of the chromosphere, and so then you just set up a kind of shock front, but it can't propagate very far because it's going down a very, very steep pressure gradient. So all the radiation has to come from a fairly squashed region inside this thing.
Yep.
And that's why you see downdraft and not an updraft, because it's squashed and it's NE squared kind of dependence on the radiation. Is that right?
Yeah, that's right. So there's a temperature, a bubble, a low density bubble, and then on either side it's a high density. And that layer, the condensation, is only like 30 kilometers in height range, which is really small.
In a way, it's like trying to pull a balloon underneath the surface of the ocean. At some point, you can't get any further.
Yeah. So eventually, the density of the condensation and the pressure, it reaches a pressure equilibrium with the very high density upper photosphere.
I'll shut up now. Thank you.
So that's something that we followed. We followed the condensation all the way until it reached pressure equilibrium here, which takes a long time to calculate with the 5F11. These shocks are very computationally intensive, several weeks or months for the Emdorf models, which I'll get to. You made a comment about the bolometric luminosity from the surface of the sun. So in Emdorf flares, which I'll get to, the bolometric luminosity from the flare can outshine the bolometric luminosity from the entire surface. So I'm running a little bit behind, but I just want to mention that this model also predicts 2 components in the singly ionized chromospheric lines. We looked at the iron 2 lines. We thought that would be a place to start. Being the lowest optical depth, it would give us constraints on the velocity field and the continuum emitting layers, which are also low optical depth. So the magnesium 2 have very high optical depth, and so it's really just you're sampling the very top layers. So you don't get to probe the velocities over all those layers, the 2 layers here, the condensation and the stationary layers. So the bottom is the model of the iron 2 line compared to the observations. There are two components. So you can just look at the pink compared to the pink. And the redshifted component comes from the condensation. The stationary component comes from the stationary flare layer. All right, there's a theoretical issue with the 5F11 beam flux. Assuming electrons and protons get the same energy at the reconnection, the electrons will speed ahead of the protons. And so there will be a charge imbalance and an electric field that forms. And that electric field is indicated by the blue downward arrow, or actually the red downward arrows. And that electric field has two effects. It takes away energy from the electron beam. And then it also accelerates ambient electrons in the loop back up to reestablish charge balance. So there are two effects that need to be modeled. And this is currently being included into the RADYN code by Joel Allred at Goddard. So there is a observational result, though, from the 90s using very high time resolution hard X-ray data. Ashwandin et al., through a series of several papers, measured the time lag between the hard X-rays at high energies and the hard X-rays at lower energies. The hard X-rays at higher energies are from the higher energy electrons, and so those should get to the chromosphere faster. And the hard X-rays from the lower energy electrons should lag because those electrons take longer. And that's what they observe. They observe a time lag. And then from that time lag, you could back out a loop length over which the electrons traversed. And the lengths are consistent with electrons being accelerated in the mid to low corona. That's an issue we're going to have to think about and keep in mind. The electrons seem to be accelerated higher up, and so there should be this electric field. All right, to summarize about solar flares, I'll just say that we're analyzing many solar flares with IRIS, and we have this new addition in the 2 flare layers, but I'm afraid I'm gonna have to try to break that model down, being a responsible scientist, by looking at other flares and see if it also holds. All right, so on to flares from other stars. Active M dwarfs produce very energetic flares, including the next star over, Proxima Centauri. This is an observation of a flare from Proxima Centauri. The U band is shown, it straddles the Balmer jump, so it's the near UV continuum. It's very impulsive, peaking early in the flare. And then the soft X-rays from, I think that's XMM, peaking later in the flare. And it's actually very similar to the timing that we observe in solar flares, where the optical emission in solar flares peaks early with the hard X-rays, and the soft X-rays from the loops peak later. We sometimes invoke loops and footpoints to describe these two light curve behaviors. Unfortunately, we can't observe hard X-rays during flares on other stars. The hard X-rays are just way too faint. The 1 over d squared diminishes them drastically. So we don't have such glorious movies of M dwarf flares. Here's M dwarf not flaring in the U band. And then on the right, M dwarf flaring by 5 magnitudes, or a factor of 100. So that's a much more energetic flare than we've ever seen on the sun. We have detailed spectral characterization of M dwarf flares. One of the largest M dwarf flares I've ever observed by my thesis advisor, Suzanne Hawley, was called the Great Flare on 80 Leo. The U-band light curve is on the left. It increased by a factor of 70. There were several peaks there and lasted several hours. They also obtained spectra around the Balmer jump. These are the first spectra really to show definitively what was happening with the continuum emission and the blending of the higher order Balmer lines. I reanalyzed these spectra for my thesis. The blue line is a black body fit, about 12,000 degrees, 10,000 in the bottom panel. And then the Balmer lines get really bright and really broad. So for solar flares, we have energy fluxes and electron beams of several times F11. And other flares with high spatial resolution data have shown even or suggested energy fluxes of greater than F12. So for M-dwarf flares, we should probably consider something that large or larger, given that these flares are just much more energetic. And when you go to simulate an F11 beam in an M-dwarf atmosphere, you get the plot on the right, which is from Joel Allred's thesis. It shows very bright Balmer continuum emission, a Balmer edge, which is not observed, and then some emission in the optical, but nothing like a hot black body. So we need to do something else. F11 does not work. 5F11 doesn't even work. 5F11 kind of looks like that. So we crank it up to F13. This is a cartoon summarizing the atmospheric evolution. It's very similar to the 5F11, except these layers are hotter. The condensation and the stationary flare layers are hotter and they're denser. And therefore, the NUV and optical continuum forms over a large optical depth. As a result of this large optical depth, the range over which the continuum emerges varies as a function of wavelength because of the wavelength-dependent opacities of hydrogen at 10,000 degrees. So if you have a large optical depth at 10,000 degrees, you should get something like a hot black body spectrum, which is what we observe. I'll show you the prediction in a second, but I just wanted to compare the 5F11 model to the F13 model in the same wavelength region. So you can just look at the black curves here. This is from 3,500 angstrom to 5,200 angstroms. 5F11, very bright Balmer lines compared to the continuum, and a large Balmer jump ratio. The spectrum, the continuum is pretty flat. The F13 has a rising continuum into the blue, like a hot black body. And the lines are broader, much broader. And they also kind of fade into the continuum, into the Balmer continuum. So the Balmer lines get fainter, broader, and they fade into a continuum. And we actually had to include another model ingredient to get that. So instead of having a sharp discontinuity at the Balmer edge, we now have a fading of the Balmer lines into a continuum. And to model that, we borrowed a prescription from the white dwarf modeling community, which basically figured this problem out in the late 80s. And this prescription is currently included in state-of-the-art 3D radiative transfer models of white dwarfs. So the Balmer lines get broad during flares, and that could be due to two things, really. Turbulence, or non-thermal broadening, or pressure broadening due to the ambient charge density in the flare chromosphere. So the electric pressure broadening is also called the Stark effect. And I have an illustration here of how that arises. So you have a hydrogen atom with an electron, and then the surrounding charge distribution creates a net electric field, which fluctuates in magnitude and direction constantly. And so this net electric field perturbs the energy levels of hydrogen and therefore broadens the lines. The energy splitting is proportional to the electric field strength F and the principal quantum number N and a Stark quantum number Q. So the higher order hydrogen lines with larger N are perturbed by larger energy. That's one of the characteristics of this electric pressure broadening. So here it is illustrated for N equals 8, 9, 10, 14, up to 14 as a function of electric field strength. So the electric field gets larger, the splitting of the different Stark states gets larger also. So there is a critical electric field, which I have circled there, for n equals 10. And at the critical field, the highest Stark state of n equals 10 overlaps with the lowest Stark state of n equals 11. And when that happens, laboratory experiments with sodium and also relativistic quantum mechanic theory predicts that there are enhanced ionization rates. So what this means is that if you have an electron in n equals 2 that's excited to n equals 10 in the presence of a critical field, the electron can cascade rapidly to the continuum and the atom is then ionized. So this cascading series of transitions, these have a name. They're called Landau-Zener transitions. And this happens very, very fast. So if you have a photon that comes along and it would ordinarily excite a bound-bound transition, n equals 2 to n equals 10. If you have a critical field, it will actually be able to photoionize the atom. So bound-bound opacity is transferred to bound-free opacity for wavelengths longer than the Balmer edge. And so there are a number of papers that have shown how to incorporate this modified opacity into radiative transfer calculations. And this comes from the white dwarf community, Doppin et al., Hummer and Mahalis. The levels that overlap, they're called dissolve levels. And so this continuum that results, this photoionization continuum opacity that results is called the dissolve level continuum. And so here it is for the F13, the standard ideal continuum opacity with the edge is the dashed line. But with the dissolve level continuum treatment, the Balmer continuum opacity extends longward to the Balmer edge and then fades into the Paschen continuum opacity. So that's the dissolve level Balmer continuum opacity. So RADYN does not include this, so we use the RH to model this. We put this dissolve level continuum opacity into the RH code and a hydrogen atom with many levels. However, the RH code we found was not equipped with the most accurate treatment of the Stark effect or this electric pressure broadening of the lines. And actually, this has been known since Johns Kroll et al. Oh, I didn't have the Johns Kroll et al. 1997. The figure on the left is from Johns Kroll et al. 1997, and they found that depending on how you approximate the electric pressure broadening profile for the hydrogen lines, you can get very different answers for the resultant broadening in your spectrum. So the Sutton et al. 1978 is the dashed dotted line, and that's an analytic approximation. And the other lines are more accurate full quantum mechanical calculations. And you can see there's a difference. Turns out there's a big difference. When you go to model the spectrum of Vega, on the right with the analytic approximations, you get the blue spectrum. And compared to the observation, which is the black, the lines are not broad enough by a lot. But when you go to include one of those accurate theoretical calculations, actually it's not any of those, it's from the Vidal et al. Treatment, you get the red, which gives much better broadening. For the sake of time, I'm going to skip over it. But that's what we put in the RH code, and now we have an accurate treatment of the broadening and this dissolve level continuum opacity. And so we get the red spectrum, the F13, compared to an observation in black there. So it has the same consistent continuum slope, but the lines are way too broad. And there are possible ways that you can get around that. This is published recently in APSHE. If you have, for an M-dwarf flare, you have certain regions of the flare during different stages of their heating. So you could have some amount producing the red spectrum here, but also another region that isn't being heated by such a high energy electron beam that has a lower charge density. So you add those together with a spatially unresolved observation, and we found out that you could actually get much more consistent line widths.
What do the lines of the other elements tell you?
So calcium 2K is a really interesting line. It responds very gradually, like the soft X-rays. And we've known that for M-dwarf flares for decades, and we haven't been able to come up with an explanation.
I'm wondering about the line widths.
Oh, line widths. Oh, so then,
The
yes.
Stark effect is
Only,
linear in
yeah,
hydrogen.
yep, only in hydrogen is the linear Stark effect important or present. So then the widths of the other lines would be due to thermal or then non-thermal, and some people say that's velocity, turbulence.
I'm just wondering if,
Yeah.
if you could probably use that to figure out the contribution from the star.
Yes, that's a great point. For calcium 2K does not broaden in flares with high spectral resolution data, much higher spectral resolution than this. And then compared to the Balmer lines, you can definitely see the difference. So yeah, that's a good way. You can make predictions for the DKIST. I think I'm running out of time, so I'm going to jump to the end of my talk. I'm going to summarize first. So I touched on all the major points. I had some more details about maybe including proton beams in the models. If you have enough protons, you might be able to neutralize these high electron beams. F13 has similar problems of F5, F11, but even greater. A much larger return current electric field. And so maybe protons, you have co-streaming protons. But the problem is the images of the sun during flares show the locations where the protons hit the atmosphere are different than where the electrons. So that's they might not be going into the same loops. Okay, so we have this new modeling prescription for the Balmer lines where we can get an unambiguous constraint on the electron density. And so before we had this ambiguity of about a factor of 5 to 10 in the electron density. For M-dwarf flares, it's important to know the electron density because we knew that we needed to produce dense regions of the atmosphere at 10,000 degrees to produce that hot black body-like spectrum. But now with this constraint on the electric pressure broadening, we know very accurately how dense. All right, so last couple minutes, I want to talk about the flares of Proxima Centauri and habitability issues. So the first, almost all of my talk was discussing the atmospheric response and the spectral signatures from accelerated particles going into the atmosphere. But accelerated particles also go away from the star as solar energetic particles, or SEPs. And these are thought to be formed at the shocks from coronal mass ejections. So recently, a Earth mass planet was discovered in the habitable zone of Proxima Centauri, which was exciting. The radial velocity curve of Proxima Centauri is shown there with the red dots. And that's how they're able to get the mass. But the interesting thing is that this habitable zone is at 5% of the Earth-Sun distance. So that means for an equal energy flare on the Sun and on Proxima Centauri, there will be 400 times the irradiation by the flare, from the flare on this planet, just by the inverse square law. So here's a schematic. Proxima Centauri in the center, the green is the habitable zone on the right, and then the Sun on the left and Mercury's orbit. So the habitable zone is getting a really good view of these flares. They have great spatial resolution. So where does Proxen fall in the scheme of things? Here's the time average flare energy release rate for M-dwarfs in red. Proxen is at the lower end tail of the distribution, and the star there. If you make an estimate for the Sun, it has about the same time average flare energy release rate. There are other M-dwarfs that produce much more energetic flares, such as DGCVN. And for Boulder Solar Day, I'm going to give a 20-minute talk on what we learned from the most energetic, hottest flare from an M-dwarf ever observed, which triggered the swift burst alert telescope. This flare reached a temperature of 300 million degrees. And we also had optical data, so we could characterize the white light emission. So people have calculated the effect of these flares in the habitable zone of M dwarfs. And they found that the near UV and the X-rays are not as drastic as the possible effect from energetic particles. Energetic particles are accelerated at coronal mass ejection shocks in the sun, but we've never been able to observe a coronal mass ejection from another star yet. So this is a simulation of an Earth-like atmosphere in the habitable zone of an M dwarf, and then assuming the coronal mass ejection from a large flare scales from the sun. So it's like a super CME. And it shows you the ozone amount over time. And the ozone becomes almost completely depleted from the atmosphere for about 50 years. And in that 50 years, there are many more flares that occur. And without ozone, the surface is pretty much exposed to the near UV light. And so there are possible drastic effects to these atmospheres. This is a simulation without a magnetic field on the planet. And this is kind of the pioneering study, Segura et al. The question, though, is that do these giant flares in active M dwarf stars also produce CMEs, like in the sun? Well, not all solar flares produce CMEs. Several S-class flares in 2014 didn't have any associated coronal mass ejections. And this was attributed to a large magnetic field strength overlying the active region, kind of confining the eruption. These active M dwarfs have very strong fields on their surface. We know this from Zeeman broadening. And so you have to wonder what the coronal environment of the magnetic field is. What are the signatures, last slide, of coronal mass ejections from other stars? Well, there was a group that met in Bern, Switzerland, that tried to figure it out. And besides, there are type 2 bursts, which are radio bursts, and that radio emission is emitted from the shock from the CME, and there are groups looking for those radio bursts. But there's also coronal dimming signatures. In solar flares, the lines from Eve of iron, highly ionized iron lines, get bright from the flare and then they dim. And that's a result of the coronal mass ejection expanding into the non-flaring corona. So I'll just leave up my slide. And I touched on all these already. And then I guess take any questions. Just wanted to thank you all again for coming and listening.
Adam, in the iris bandpass that you showed, there are two lines that you didn't mention. One is an iron 12 line, coronal forbidden line of iron 12, and the other is iron 21, both between carbon 2 and silicon 4 lines. Wouldn't those provide an additional constraint on your models?
Absolutely, yes. And in fact, we want to synthesize the iron 21 especially, because our 5F11 model produces very large upflow velocities, like 1,000 kilometers a second. And that's larger than what's been inferred from chromospheric evaporation in the past. And so, yes, we definitely want to incorporate iron 21. It's that by just doing iron 2 and the continuum, it took up like 30 pages in AppJ. And so we want to bring the far UV constraints in also, especially with this upflow, very large upflow velocities that are in our models. It's interesting because the upflow velocities happen, but you have to wonder, are those the regions that are upflowing with such high velocity, are they the regions that are producing the emission you see? Because it's weighted by the density. And so the very densest upflowing regions are at only several hundred kilometers a second. So we really have to do the calculation for it.
Michael?
I understand that the interpretation of how these M-star flares are coming about are pretty straightforward from the radiated signatures that you have. On the other hand, what is the level of understanding on the kind of magnetic field configurations that you have to build up on a star like that?
So we can get constraints on the magnetic energy that you need to power, say, an F-13 beam through some simple, just plug and chug magnetic energy and an Alfvén speed, and you get some energy flux of reconnected energy. And that turns out that we require about 1.5 kilogauss in the corona of these M stars to get an F-13 beam.
That's a pretty high field strength to have in a corona, isn't it?
Yes, yes. We don't have constraints on the coronal magnetic field for M dwarfs besides from confinement arguments for soft X-ray emitting plasma in flares. But we do have measurements of the Zeeman broadening and iron 1 lines, which show that 4 kilogauss fields cover about 50% of the surfaces of these stars.
Yeah, okay, this is all deduced from the observations, and I'm not saying that I doubt that.
Mm-hmm.
That is the reality. On the other hand, are there any attempts of forward modeling such fields? From how they are produced?
In the interior.
Yeah.
At CU, yes, there's a big group doing magnetic dynamo, and there's a group, Matt Browning's group in the UK is doing fully convective star dynamo. I think the problem is that they can form large magnetic fields in the interior, but it's getting them out, having them rise, become buoyant, and then.
Okay.
So there's a region, there's a disconnect between the two. But that is something that would be very interesting to simulate from dynamo to magnetic to flux emergence, and then see if the amount of 4 kilogauss field strength matches the amount you infer from the broadening and the iron 1 lines.
I just want to follow up Michael's question. Of course, if that 4 kilogauss is all in potential field, then it amounts to 0. So
yeah.
you're really, this is really, I think, a tall order.
Yeah.
For a disordered thing like an M dwarf, if we understand convection and things in these kind of things, goodness knows what the rotation profile, differential rotation looks like. So I don't know if the free energy is going to be anywhere near what you need for this kind of thing. The second point is, your interesting slide of the ozone presumes that you've got oxygen in the atmosphere to make ozone.
Yes, yes.
And of course that presumes you've got life. So you've got to catch, because there's no oxygen in the atmosphere without biology as far as we know. So to get ozone at all, you have to have life, and then you can kill the life off because you then make ozone, you need ozone to protect you, but then the life is exposed to UV, so it's like a catch-22 situation. An M dwarf doesn't sound like a good place to start doing anything with life.
There
May
are
I take exception to that?
Yeah.
It might be that the flares would allow life to prosper on such a planet because, you know, if you think of an M dwarf, it has a very red radiation field, and that's not going to be very useful for photosynthesis. You need some blue light. I mean, if you think that, you know, life develops much as the way it did on the Earth, and you need a photosynthetic energy generation.
You know, when they put teeth inside things in dentists, things and tools, they use ultraviolet light to kill all the bugs off. So I think you're screwed.
I mean, if you have an ocean, I mean, would the water shield you well enough? I mean, stuff at the surface might be
Yeah, it might be
killed off,
blue-fried.
but if you have something living deeper in an ocean, it might
That's where
survive.
the origin of life on Earth is
Yeah.
started from.
The origin of life on Earth started through the onset of these things called methanogens. And so we got started probably through a sulfur route, chemistry route. And then after a while, there was a huge onset of oxygenation about a billion years after or something like this. Mark, you know about this stuff. You're teaching this stuff. So I'm struck by this funny fact.
I don't know if it's so certain how
Yeah.
life started. I mean, that's,
Oh, no, no, no.
that's one possibility.
No. But I think that we should pursue life in any way, but we should not overstate the case. I mean, the basic problem in science right now is that overstatement gets great rewards, and that's going to come back and bite us in the ass at some point. And I'm seriously worried about that. I think a little bit of conservative behavior about how we might go forward in science is called for. So attaching everything to the origin of life is not a productive way of going, I don't think.
Just one comment, just follow up on the discussion is, there's been some recent photochemical modeling showing that you can have abiotic production of ozone. Far UV Lyman alpha can, I think, dissociate carbon dioxide and then lead to ozone. It's not due to life. So.
Mark, did you have another question or comment?
Oh, I was just going to ask, do we see spots on Proxima Centauri? Because, this question, getting back to Michael's question about what the structure of the surface field is.
Yeah.
Is there evidence for large-scale flux emergence, like loops, or is it in a more complex state?
I think there's both. There's two ways of large-scale fields are measured by the ZDI, and then the small-scale fields by Zeeman broadening. And the Zeeman broadening showed that Proxen has a surface average field strength of 600 Gauss. So lower field strength than some of these other active M dwarfs, but much higher than the sun.
But were you not finding? You said you were finding more flares than CMEs. Is that right? That you were not finding CMEs.
Oh, so no one has found them yet. They're looking for them. Yes. Yes.
Does that suggest there might not be big whopping loops that might be a more complicated field that's reconnecting and making flares?
The observational monitoring so far has been really limited. There's been 2 groups and 1 paper published on it, and they looked in the radio frequency range that you'd think you'd need to see these type 2 bursts, and they didn't see any in that frequency range, but that was only for so many hours of monitoring. And did you catch a big enough flare, and it's kind of a tricky problem at this stage because you really need a lot of monitoring time to nail down all the parameter space. Yes?
I think Michael is going to be the last question comment.
Okay.
He's going to be around, well, you can find him.
So now,
I know where he lives.
there is, of course, with the detection of these eclipsing planets, the sort of non-traditional extra source of information about the star and the structure of the atmosphere of the star, and that is that in principle, I mean, that has been shown with other eclipsing events of planets around other stars. We could use, like the Hubble STIS, to deduce a center to limb variation that is different in the blue as compared to in the red, and in this way you could characterize the star to much higher accuracy than traditionally. Could this be done with Proxima Centauri?
The transit, so they've looked for transits, and so far they haven't found the transits. They detected the planet from the radial velocity wobble. So the system could be inclined such that it wouldn't even transit the star. But they are still looking for that, and I'm sure that TESS will be digging away. TESS is transiting. It's like Kepler, but for brighter stars, and so they'll be looking at Proxima, I'm sure, just until they find something or definitively ruled it out.
What are the odds that the whatever planets are orbit Proxima or transiting?
Sorry?
What are the odds that whatever planets orbit Proxima are transiting? Is it like 1 in 100 or something?
People have worked this out. I'm sorry, I don't know off the top of my head, but it's they've calculated this. Sorry.
All right, I'd like to close the colloquium at this point, so thanks.
Okay, thanks.
Again.